Typical test, typical test. Hello, hello, hello. Can I hear myself? Yes, but through the wrong audio. Let's try that again. Hello, hello, hello. Awesome. Okay, cool. So, been a while, but let's just crack on. Happy New Year. And Duolingo, Greek. I think I want to finish Greek. Here we go. So, let's go straight into the which the course. Select the characters for ga. Ga, ga. To cigaro, cigaro. The cigarette. Yes, the mango. Ne. Do manco. Yeah, that looks about right. Select the matching pairs. Ga. Ga. Me. Me. A. Gos. Gos. Ni. Nivi. Oh. Yeah. 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 Su. Mark. Yeah. What's that then? That's maybe with. Oh, it's hello. Yeah. Yeah. With. Mark. Su. Yasu. Hello, Mark. Yasu. Yasu Mark. Okay, that's interesting. And this character here is very interesting. Let me just take a look at this properly. If Windows isn't shit and lets me actually pick my language. Really? Are we doing this right now? I can't change my language. Let's try bringing this up. Try now. Nope. Let's check regional settings. One day, eh? I'll just be able to focus. It'll be awesome. Yep, Greek is there. Apparently I can't use it. Well, that's great. It's awesome. Okay, well, whatever. Ja su mark. Okay, the gyro. O. Gyros. 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 Jana ketomanko. Anna. It's the mango. Anna and the mango. K. Okay, yeah, I know that. I knew that. Hello, Mark. Sesu Mark. Okay. Gos. Gos. Ogieros. Ogieros. O is the gyro. Gyros. Wow. Ooh, that's really hard. Hang on. Haha. I can't quite separate those words. This is the last one. Omicron's in there. Adras. So. Let's just check it. It's wrong, but I couldn't quite catch it. Yine. γυναίκα και ο άντρας.
Η γυναίκα και ο άντρας.
Η γυναίκα και ο
Η γυναίκα και ο άντρας. Ήτα, γυναίκα και όμικρον άντρας.
Oh, I see. When you do the slow one, it actually says the letters.
Η γυναίκα και ο άντρας.
Η γυναίκα και ο άντρας. The woman and the man. Γυναίκα και ο άντρας. Ooh, that's difficult. Okay, that's interesting. I won't get that next time. The man is andras. I think it's that. To. Andras.
Άντρας.
Adras. With is me, the cigarette, or cigaro. Let's see. Giros. Cigaro.
Τσιγάρο.
Ah, so it's the other way around. So, the man with the cigarette. The man with the cigarette. Let's just look at the discussion there. Why is it that way around again? What's the difference with O and 2? And is the T in silent? Andras is being pronounced as Andras, I think. How do you know when the letter represents the sound of D? O is used for masculine nouns, and 2 is used for neuter nouns. Masculine nouns, okay, the man. So it'd be the other way around, okay.
Η Κάρμεν και η γυναίκα.
Whoa.
Ήτα, Κάρμεν και ήτα, γυναίκα. Η Κάρμεν και η γυναίκα. Η Κάρμεν και η γυναίκα. Και άντρας.
Oh, this is hard, okay.
Ήτα,
Ita,
Κάρμεν,
Carmen.
Ita.
So, Carmen,
Ήτα,
Ita,
Κάρμεν
Carmen,
και
que,
ήτα,
Ita,
γυναίκα.
Ineca.
Γυναίκα. Η Κάρμεν και η γυναίκα.
Carmen que Ineca. Carmen and the woman. Okay, wow, I did not hear those letters. The man, which is O, aftos,
Άντρας.
atrás, the
Το.
woman. The woman was Ginaka.
Γυναίκα.
Okay, I see. Gineka to nero. Okay. O antas Gineka to nero.
Η Άννα και το μάγκο.
Hiana que to mango. It's Anna and the mango. Hannah Gedo mango.
Η γυναίκα και ο άντρας.
Menko? No, that's Gineka
Η γυναίκα και ο άντρας.
que o natras.
Ήτα,
Yita,
γυναίκα
Gineka
και
que Omicron
άντρας.
atras. Atrás. The woman and the man. Atrás. The man with the cigarette. O. Nie. Antras. Antras.
Άντρας.
Atrás. With. Me. To. Cigaro. Ko. Manco. Cigaro.
Τσιγάρο.
Cigaro. Ο άντρας με τον τσιγάρο.
Η Κάρμεν και η γυναίκα. Ήτα.
Ήτα,
Κάρμεν.
Carmen, Carmen
Ήτα.
και Ήτα,
Γυναίκα.
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 Γυναίκα. Carmen and the woman. Ooh, that was difficult. Wow, wow, wow. Okay. That was difficult. Right. Good stuff. I like that. That was very difficult. So, what am I doing? Yes, I've been looking at the Schrodinger equation, I guess. I can't quite remember, but we know the Schrodinger equation. We're just a little bit confused or confuzzled or, you know, bewildered, baffled by what data goes in to the wave function, where wave function either takes an x or outputs an x and is of time. So this is a partial differential equation because of the little curly d, and that's why we've got the two variables in the function, I guess. The thing is, I've been doing some research, and this is a bit old hat because it doesn't take into account general relativity, the curvature of the Earth, curvature of the solar system, the universe, and everything. The dude who did that was apparently Dirac, which is a bit weird because I thought that quantum did not work alongside general relativity, but hey, what do I know? So let's just have a quick recap. I'm a little bit tired as always, but let's see if we can go through this a little bit. And I'm coming up to the end of my little book where I've got my lovely bits of work. I'm very proud of actually filling out a book for once with stuff. And my friend has bought me this gorgeous new book. So I think we'll start this one with the Dirac equation. I'll go to the pub and start to ponder after we've had a look here. So thank you so much. I'm going to look through these tabs because they might be interesting, and then we'll just go straight on to checking out Dirac's equation, which I seem to remember there's some sum of three iterations. N equals 1 to 3. You've got some mass times c squared plus c, or multiplied by c. I think it's plus c. And then I think you have the imaginary number at the beginning. But we shall see. So, introduction to eigenstates. What's an eigenstate? Higgs boson, if I know. Because of the uncertainty principle, statements about both the position and momentum of particles can only assign a probability that the position or momentum will have some numerical value. The uncertainty principle also says that eliminating uncertainty about position maximizes uncertainty about momentum. We know that. You and me know that. And eliminating uncertainty about momentum maximizes uncertainty about position. Ooh, that's bitter. That is bitter. It's nice though, lemongrass. A probability distribution assigns probabilities to all possible values of position and momentum. Okay. Schrodinger's wave equation gives wave function solutions. Schrodinger's wave equation gives wave function solutions. the squares of which are probabilities of where the electron might be, just as Heisenberg's probability distribution does. I don't think I knew that. I don't think I knew that. In the everyday world, it is natural and intuitive to think of every object being in its own eigenstate. Explain it, please. This is another way of saying that every object appears to have a definite position, a definite momentum, a definite measured value, and a definite time of occurrence. However, the uncertainty principle says that it is impossible to measure the exact value for the momentum of a particle like an electron, given that its position has been determined at a given instant. Likewise, it is impossible to determine the exact location of that particle once its momentum has been measured at a particular instant. Therefore, it became necessary to formulate clearly the difference between the state of something that is uncertain, in the way just described, such as an electron in a probability cloud, and the state of something having a definite value. When an object can definitely pin down in some respect, it is said to possess an eigenstate. An eigenstate is a definite position. Could have just said that. As stated above, when the wave function collapses because the position of an electron has been determined, the electron's state becomes an eigenstate of position, meaning that its position has a known value, an eigenvalue of the eigenstate of position, an eigenvalue of the definite position. The word eigenstate is derived from the German or Dutch word eigen, meaning inherent or characteristic. An eigenstate is the measured state of some... Jesus Christ, James. Okay. I'm sorry. I've had a few beers. An eigenstate is the measured state of some object. An eigenstate is the measured state of some object possessing quantifiable characteristics such as position, momentum, etc. etc. The state being measured and described must be observable, i.e., something such as position or momentum that can be experimentally measured either directly or indirectly, and must have a definite value called an eigenvalue. Eigenvalue also refers to a mathematical property of square matrices, a usage pioneered by the mathematician Hilbert in 1904. Some such matrices are called self-adjoint operators and represent observables in quantum mechanics. Gone. Okay. Inner product space. In mathematics, an inner product space, or rarely a Hausdorff pre-Hilbert space, is a real vector space, real being the real number, or a complex vector space, complex being the imaginary numbers, with an operation called an inner product. Inner product, product, multiplication, inner, don't know. The inner product of two vectors in the space is a scalar. 0 to 1. No, 1. Scalar, 1. An element of a field which is used to define a vector space. A quantity described by multiple scalars, such as having both direction and magnitude, is called a vector. My apologies, I should know this. A scalar is an element of a field which is used to define a vector space. A quantity described by multiple scalars, such as having both direction and magnitude, is called a vector. Great, doesn't help. The inner product of two vectors in the space is a scalar, often denoted with angle brackets such as bra and ket. A, B. Vectors, quantum vectors. Inner products allow formal definitions of intuitive geometric notions. Inner products allow formal definitions of intuitive geometric notions. No idea, such as lengths, angles, and the orthogonality. Zero inner product of vectors. Inner product spaces generalize Euclidean vector spaces. Inner product spaces of infinite... Inner product spaces generalize Euclidean vector spaces. Inner product spaces generalize Euclidean vector spaces. Okay, don't care. In which the inner product is the dot product or scalar product of Cartesian coordinates. dot product this one here from -1 to 1. Inner product spaces of infinite dimension are widely used in functional analysis. Great, good for you. Field mathematics. In mathematics, a field is a set on which addition, subtraction, multiplication, and division are defined and behave as the corresponding operations on rational and real numbers do. A field is thus a fundamental algebraic structure which is widely used in algebra, number theory, and blah blah blah. Okay, we understand. Conjugate mathematics. Conjugate is a negation of something. So if you've got a plus b, it would become a minus b, something like that. A math conjugate is formed by changing the sign between two terms in a binomial. Binomial. Damn. Binomial. By two nomial number. Two numbers. Binomial. A mathematical expression consists of two terms connected by a plus sign or a minus sign. Okay, cool, good. Inner product space. Just read that, I swear. Inner product. Yeah, okay. What does the C mean in maths? C indicates a complex number. Born rule. The Born rule is a key postulate of quantum mechanics which gives the probability that a measurement of a quantum system will yield a given result. In its simplest form, it states that the probability density of finding a particle at a given point when measured is proportional to the square of the magnitude. The square of the magnitude of the magnitude of the particle's wave function at that point. Magnitude, the length of it, something like that. Let me just read that again. In its simplest form, it states that the probability density somewhere here of finding a particle at a given point, probability density of finding in a given point when measured is proportional to the square of the magnitude of the particle's wave function at that point. Max Born, 1926. Cool, Schrodinger Equation. Moving on. Exponent rules, good. Hertz to kilograms, good. Mass of electron, 9.1 to the power of 10 to the minus 31, good. Okay, got it. Planck's constant, 6.6, 9.1 to 10 to the power of 31, minus 31. 10 to the power of minus 31, 9.1, 10 to the power of minus 31, 6.6, 10 to the minus 34, Planck's constant. Okay, Planck's constant is the energy that it takes to emit an electron. Something like that. There's more to this. I need to figure this out. But anyway, Hertz, great. Don't remember. Ooh, okay. Dirac eigenvalue, I like it. Dirac eigenvalue. That makes some sense now. Okay. Electron volt, EV, okay, in physics. National Institute of Standards and Technology, some specific information about the ion of hydrogen and something. Dunno. Lots of 1985 websites. Theory and theoretical input data, cool, don't care. NIST. Oh, NIST, okay, that's what it is. Respect. Good. Yeah, we like this page. Awesome periodic table, always good. And a hydrogen atom with stuff. Right, okay. So, where were we? So we just read all that, learned some cool stuff. Let's look at Dirac's equation. Here's a guess, because I always like to guess first. Make myself look like an idiot. And then we'll see how right I am. I think it is something like mc squared plus c. Then it's a partial differential. I think it's over the partial of t with a wave of xt, but I think this is mi. Now I swear there's a p, there's a momentum and an angular, so like that, and I think that is n, so that's going to be sum of 3 n. We forget that we love this program. Let's try that again. It's going to be something like this. n equals 1. So this is going to be mc squared plus c times, maybe this is I, all multiplied by the partial of t with respect to x of t. Something like that, I think. Let's get rid of this one. Ugly. I think it's something like that, but I've got something wrong. Not sure what it is yet. I don't think that I belongs there. And I think there's a missing term on this. Because if it's a partial differential of what? It's a partial differential of maybe this over t? I don't think so. Anyway, let's go and have a look at it then. Good to just joggle the brain. Dirac equation. Let's do this. Okay. Beta. Yes, that's the one I never understood. Okay, let's just get this down then. So we've got our c, and we did a plus, but we've got a c squared in here. Bm. Okay, fair enough. Maybe beta is the imaginary part. Maybe you aren't so wrong. mc squared plus c to the sum of 3, n equals 1 to 3. Acceleration, momentum, mass times velocity, acceleration plus. Yeah, exactly, yeah. And then multiplied by, ooh, so there is not a partial differential here. It is just this. Interesting. I don't think I would have remembered that. Okay, cool. Let's go for it. Dirac's equation. Right. Let's learn a bit about Dirac. In particle physics, to make sure I can hear myself here. Good, I can. Grace. Right. In particle physics, the Dirac equation is a relativistic wave equation derived by British physicist Paul Dirac in 1928. British, really? Are we really that good? I don't think so. In its free form, or including in its free form, in its free form, what does that mean? I don't know what free form means. We'll look at it later. Or including electromagnetic interactions. It describes all spin 1/2 massive particles. Spin half massive particles such as electrons and quarks for which parity is a symmetry. It is consistent with both the principles of quantum mechanics and the theory of special relativity, and was the first theory to account fully for special relativity in the context of quantum mechanics. It was validated by accounting for the fine details of the hydrogen spectrum in a completely rigorous way. Wow, okay, sounds good. No idea what it means. The equation also implied the existence of a new form of matter, antimatter. Yes, we knew that. I knew that. You didn't know that because I'd not talked about it before. Previously unsuspected and unobserved, and which was experimentally confirmed several years later. It also provided a theoretical justification for the introduction of several component wave functions in Pauli's phenomenological theory of spin. Phenomenological. This is a joke. The wave functions in the Dirac theory are vectors, that makes sense, of 4 complex numbers known as bispinors. Let's get a little image going. A vector with 4 imaginary numbers. So we've got a vector x, y, z, a. just do that. So that's a vector. But these are all imaginary. This is an imaginary element. These ones. What does that mean? Let's take imaginary again. If we've got, this is x minus x, I minus I, and I is equal to square root of -1. No, I squared. I squared is equal to -1? Is that right? Can't remember. Let's do it. I squared. Can't type. Oh my god, I can't type. I squared equal to -1. I squared equals -1. Square root of -1, or the square root of -1. Why is I squared equal to -1? Great. Okay, cool. So that is the idea there. So if I squared, so I times I is equal to -1. I squared is equal to -1. Then we can start plotting this as Okay, I'm not that good mathematically yet. I need to have a good think about that. How can we plot this? Well, let's imagine it in Cartesian at the moment. Euclidean? Whatever, who cares? Let's imagine it like this at the moment. So we've got this x, and we've got y, and we've got z. And we shall go, what? Where's the fourth? Well, if we plot 1, 2, 3, and then 4, what does that come out as? So we've got 1 on the x, boom, 2 on the y, boom, dunk, dunk, and then 3 on the z up here. So we've got a point up here. And then we've got this fourth thing happening. Okay, that's interesting. Good to imagine anyway. Let's just block this up a bit. So it says, the wave functions in the Dirac theory are vectors of 4 complex numbers known as bispinners, 2 spinners, 2 of which resemble the Pauli wave function in the normal and the non-relativistic limit. 2 of which, so 4 complex numbers, 2 of which resemble the Pauli wave function in the non-relativistic limit. Pauli wave function in the non-relativistic limit. I don't know what that means. In contrast to the Schrodinger equation, which described wave functions of only one complex value. Don't know what it means. Moreover, in the limit of zero mass, the Dirac equation reduces to the Weyl equation. Oh look, that's a Feynman diagram. Cool. We like Feynman diagrams. There it is. In physics, particularly in quantum field theory, the Weyl equation is a relativistic wave equation for describing massless spin-half particles called Weyl fermions. Weyl fermions. The equation is named after Hermann Weyl. The Weyl fermions are one of the 3 possible types of elementary fermions, the other 2 being the Dirac and the Majorana fermions. None of the elementary particles in the Standard Model are Weyl fermions. previous to the confirmation of the neutrino oscillations, it was considered possible that the neutrino, which I think is a particular subset of an atom, so another quark kind of thing, is one of those like quantum periodic table things, the neutrino. Possible that the neutrino might be a Weyl fermion. It is now expected to be either Dirac or a Majorana fermion. Majorana? Good guess. In condensed matter physics, okay, some materials that can display quasi-particles that behave as Weyl fermions, leading to the notion of Weyl semi-metals. I swear this is all just made up. My god. Okay. Mathematically, any Dirac fermion can be decomposed as two Weyl fermions. Any Dirac fermion can be decomposed as two Weyl fermions, and the Weyl fermion is relativistic wave equation of opposite chirality coupled by the mass term. Chirality, chiral, is that a spin? Chiral is symmetry. Let's just get a definition of chiral. Property of without symmetry, important in several branches of science. Without symmetry. Okay. So we went from the Dirac equation, we got into this Weyl equation. We didn't finish this sentence off, so let's just carry on. And we're going to go over this, and we have to understand all this before we move on, I think. So, okay. Although Dirac did not at first fully appreciate the importance of his results, the entailed explanation of spin as a consequence of the union of quantum mechanics and relativity, the explanation that came from it of spin as a consequence of the union of quantum mechanics, so this imaginary number prediction probability of position and relativity, curvature, and the eventual discovery of the positron, a positive something, represents one of the great triumphs of theoretical physics. This accomplishment has been described as fully on a par with the works of Newton, Isaac Newton, Maxwell. Maxwell is charges and stuff, I think, and Einstein before him. In the context of quantum field theory, the Dirac equation is reinterpreted to describe quantum fields corresponding to spin-half particles. The Dirac equation appears in, yeah, we know that, Westminster Abbey. And here is that beauty. Oh, look, it's equal to the Schrodinger equation. Okay, it's equal to the Schrodinger equation. So it is a derivation of it. Of some sorts. Discretizing God. Okay. So let's reread this. Go one by one through the blues. And we will get to the bottom of this. Oh look, it is slightly different actually. Yes, because the Schrodinger equation has this bracket of the wave function. So the wave function of time, or in relationship of time, is a vector is a complex vector. I can't remember. Okay, so let's try this again. Let's close this down. Let's go for it. Let's be all about this. In particle physics, in the physics of a particle, the Dirac equation is a relativistic wave equation. Relativistic. I think it comes from that relationship between energy, mass, and the speed of the constant light. I think that's why it's called relativistic. Let's just double check. Relativistic wave equations, relativistic quantum field equations, quantum field equations, field being the place where you can do operations on sets of numbers, sets being this kind of thing. Here's a set. That is I call this a pube in code. Let's say this is the set of A, B, and C, and it is saying that if we add S1 and S2, A, B, C, then S1 plus S2 is a field. Right, let's just double check that. So, well, it is one of all possibilities of fields, which is minus multiplication and division. So, mathematics, field, set on which addition, subtraction, multiplication, and division are defined and behave as the corresponding operations on rational and real numbers. Rational and real numbers. Oh, gonna have to look at rational again. In mathematics, a rational number is a number that can be expressed as a quotient or fraction. As a fraction, people know the word fraction. What's the difference between fraction and quotient? Quotient, quotients, how many times is a quantity produced by division of two numbers? Fucking hell. So, okay, whatever. In mathematics, a rational number is a number that can be expressed as the fraction p over q of two integers, a numerator p and a non-zero denominator. Ha, okay, yes. Q. That's a quotient. No, that's a rational number. Rational number is a fraction. Okay, rational number is a fraction. Okay, no, okay. Let's go back to this. Oops. Relativistic quantum field equation of here. In physics specific. Okay, in physics, specifically relativistic quantum mechanics. Relativistic quantum mechanics and its applications to particle physics. Relativistic wave equations predict the behavior of particles at high energies, high enough to emit Planck's constant, no doubt, and velocities comparable to the speed of light. Energies and velocities comparable to the speed of light is relativistic wave equations predict the behavior of particles at high energies and velocities comparable to the speed of light. C. In the context of quantum field theory, all of those operations, there's a theory about them. Okay, the equations determine the variables of quantum fields. The equations determine the variability of a quantum field. I don't understand what that means. The solutions to the equations, universally denoted as psi, or psi, Greek psi, are referred to as wave functions. In the context of relativistic quantum mechanics, and fields in context of quantum field theory. The equations themselves are called wave equations or field equations because they have the mathematical form of a wave equation form of a wave equation, or are generated from a Lagrangian density. And the field theoretic Euler-Lagrange equations. See classical field theory for background. The equations themselves are called wave equations or field equations because they have the mathematical form of a wave equation or are generated from a Lagrangian density. So Lagrangian's this guy, and a density, what is this? Is a density of probability? Okay, let's go into that. Lagrangian field theory is a formalism in classical field theory. It's a formalism. So it's like an equation of a classical field theory. It is the field theoretic analog of Lagrangian mechanics. Lagrangian mechanics is used to analyze the motion of a system of discrete particles, each with a finite number of degrees of freedom, 3 let's say. Lagrangian field theory applies to continua and fields. Please, this is not 18 bloody 20. Keep going. No. Continua in physics. Continuum mechanics is a branch of mechanics that deals with the mechanical behavior of materials modeled as a continuous mass rather than as discrete particles. I see. Yes, well, let's imagine that. Let's imagine a cylinder, and we have a continua because this entire thing is taken into account rather than all of its subcomponents, which are little turds, also known as particles. We don't care about the interactions between these, we care about the interactions on the whole continua. The whole object. Okay, I think that's what that means. Let's just imagine that's what that means. Which have an infinite number of degrees of freedom. Lagrangian field theory applies to whole objects and fields, which have an infinite number of degrees of freedom. One motivation for the development of the Lagrangian formalism on fields, and more generally for classical field theory, is to provide a clean mathematical foundation for quantum field theory, which is infamously beset by formal difficulties that make it unacceptable as mathematical theory. The Lagrangians presented here are identical to their quantum equivalents, but in treating the fields as classical fields, instead of being quantized, okay, roughly understand that, one can provide definitions and obtain solutions with properties compatible with the conventional formal approach to the mathematics of partial differential equations. That's a lot. The Lagrangians, let's just highlight that. The Lagrangians presented here are identical to their quantum equivalents. But in treating the fields as classical fields, instead of being quantized, one can provide definitions and obtain solutions with properties compatible with the conventional formal approach to the mathematics of partial differential equations. What does that even mean? One more time. The stuff presented here, the stuff here are the same as their quantum equivalents. But in treating the fields as classical fields, instead of being quantized, in treating the fields as classical fields, one can provide definitions and obtain solutions with properties compatible with a conventional formal approach to the mathematics of partial differential equations. Yeah, okay, I see. I see. I wonder if it's because, I mean, it doesn't say, but maybe it's because there is no I, there's no complexity, there's no complex number in it, because it is classical. Hard to tell, hard to tell. This enables the formulation of solutions on spaces with well-characterized properties, such as Sobolev spaces. Sobolev spaces. Let's take a look. In mathematics, a Sobolev space is a vector space, okay, Euclidean, let's say, of functions equipped with a norm. This isn't a normal, it's a norm. So a norm is something like what? A normed vector space or normed space is a vector space over the real or complex numbers on which a norm is defined. Vector space over real or complex numbers on which a norm is defined. A norm is the formalization and the generalization to real vector spaces of the intuitive notion of length in the real world. A norm is a real valued function defined on the vector space that is commonly denoted x leads to the magnitude of x and has the following properties. It is non-negative, meaning that the magnitude of x is always greater than or equal to 0 for every vector x. It is positive on non-zero vectors, that is, the magnitude of x equals 0, which implies x must equal 0. Magnitude of x is equal to 0 implies the magnitude of x is equal to 0 implies that x equals 0. Right, I see. Yes. Because it ain't multiplied by anything, so it's got to be 0. For every vector x and every scalar alpha, alpha multiplied by x is equal to the magnitude of a and x. The product of a and x is equal to the absolute value of alpha multiplied by the magnitude of x. Wow. Yeah, I was just checking to make sure everything's okay. Let me read that again. For every vector x and every scalar alpha, the magnitude of the product of alpha and x is equal to the absolute value of alpha, 2, let's say, multiplied by the magnitude of x. So magnitude of x is equal to 0, so it's going to be 0. 1 times 0. It is positive on non-zero vectors. Fine, these are like axioms. The triangle inequality holds, that is, for every vectors x and y. The magnitude of x plus y is x plus y, that's a vector. The magnitude of it, this one, is equal to, no, is less than or equal to the magnitude of x, this, plus the magnitude of y. It's greater than or equal to. That's interesting. You'd imagine it's always equal to. Anyway, okay, doesn't matter. A norm induces a distance called its norm-induced metric by the formula d, the function of d of x, y is equal to the magnitude of y minus x, okay, which make any normed vector space into a metric space. So what is this again in math? A normed vector space, or normed space, is a vector space over the real or complex numbers in which a norm is defined. It doesn't make sense to me. Okay, lots to learn. A Sobolev space is a vector space of functions equipped with a norm that is a combination of L super P, so LP hyphen norms. In mathematics, the LP spaces are function spaces defined using a natural generalization of the P norm for finite dimensional vector spaces. Finite dimensional, not infinite, vector spaces. They're sometimes called Lebesgue spaces, named after Henri Lebesgue. According to the Bourbaki group, they were first introduced by something. Okay. Let's read this again. Sobolev space is a vector space of functions equipped with a norm. Okay, norm. Fair enough. That is a real or complex vector space. That is a combination of LP norms of the function together with its derivatives. The change in direction of slope up to a given order. 1, 2, 3, n order. Derivatives are understood in a suitable weak sense to make the space complete, i.e. a Banach space. Oh my god, I'm not doing this. No more spaces, for goodness sakes. Where did we go? It enables various theorems to be provided, ranging from proofs. Let's just see if this helps. So this enables the formulation of solutions on spaces with well-characterized properties, such as Sobolev spaces. Well-characterized properties, because they're based on a norm space which is real or complex. Norm. Characterized properties. It enables various theorems to be provided, ranging from proofs of existence to the uniform convergence of formal series to the general settings of potential theory. In addition, insight and clarity is obtained by generalizations to Riemannian manifolds and fiber bundles. Can't remember what Riemannian is, but I know that a fiber bundle is a way of denoting a variable metric, miles per hour, kilograms, on a usual graph. So you've got your line at the bottom and you have this fiber up, and that fiber at some point has some gauge to it, a variable metric, something like that, a fiber bundle. We'll look into it. Allowing the oh, by the way, Riemannian manifolds and fiber bundles, please check out Tim Nguyen from Google. He's got actually great videos on them. I have watched them. I found them great. I've forgotten them. I'm going to watch them again. Please do that. In addition, insight and clarity is obtained by generalizations to Riemannian manifolds and fiber bundles, allowing the geometric structure to be clearly discerned and disentangled from the corresponding equations of motion. A clearer view of the geometric structure has in turn allowed highly abstract theorems from geometry to be used to gain insight, ranging from the Chern, Gauss, Bonnet theorem, and the Riemann-Roch theorem, Riemann-Roch, to the Atiyah-Singer index theorem, and Chern-Kern-Simon's theory. Okay, it doesn't say much to me. So we're at relativistic wave equations. We managed to go on to that stuff. So, okay. So relativistic wave equation is what? Honestly. Predict the behavior of particles at high energies and velocities compared to the speed of light. Okay, back to the Dirac equation. So the Dirac equation is a relativistic wave equation relative to the speed of light, derived by British physicist Paul Dirac. In particle physics, the Dirac equation is something related to the speed of light whether it be energy or velocity. And it was derived by Paul Dirac in 1928. All of that, just for that first sentence. In its free form, here we go again. Number 2. In its free form. Whoa! Maths, okay. Okie dokie. Covariant form and relativistic invariance. Invariance. In? Variance. Is it with variance? Invariance. That's the etymology of that. Etymology, invariance. Remaining always the same, not varying or changing, without change. Invariant. It's avariant. Covariant. Etymology. See, co is with, paired with variance, tending to change. So this is to demonstrate. Nope. Yep. Covariant. So with form and relativistic non-changing. To demonstrate the non-changing of the equation, it is advantageous to cast it into a form in which the space and time derivatives, great, glad that is working as always, the space and time derivatives appear on an equal footing. Yes. This reminds you of that gauge theory and fiber bundling that that we've been talking about. Covariant form, relativistic invariance. To demonstrate the relativistic invariance of the equation, it is advantageous to cast it into a form in which the space and time derivatives appear on an equal footing. Space and time derivatives, that means any change in time, so time is going from x to x plus n, and any derivative, so that's going to be going up, let's say in I, so it's increasing in I, and that increase is equal to the space that it's present in. Space, let's say the space of x and y, let's say that we are adjusting by to x1, y1, or xn, yn. This derivative must, regardless of its amount, let's imagine n is equal to not I. Let's imagine that. But it doesn't matter. It's saying that I and not I must equal each other in terms of the derivative. They must equal 1. They must equal the same. They must be equal. To demonstrate the relativistic invariance of the equation, it is advantageous to cast it into a form in which the space and time derivatives appear on an equal footing. New matrices are introduced as follows. D is equal to this fucker post 0. Don't worry, I'll just get my Greek keyboard up. Oh, it's not working, that's right. I remember now. Let's get it. It's what is that symbol? That is, it's not alpha, it's not beta, it's not C, it's not delta. It's E, I, L, it's not lambda. Yeah, Greek letters. Let's get a name for it because I'd like to remember this. It is it is E. It's this fucker, isn't it? Because they've done a weird version of it, but it's gamma. Yeah, gamma. Okay, so it's D is equal to gamma post 0, comma, A is, so this is a set, is it? A is equal to the complex gamma post 1, B is equal to the complex gamma 2, C gamma 3. New matrix is introduced as follows. And the equation takes the form, remembering the definition of the covariant with changing components of the 4 gradient, and especially that partial derivative partial of 0 is equal to 1 over c multiplied by the partial of t. Let me just sit down. Let me sit down here. Ah, itchy nose. Okay, wow. Okay, wasn't ready for this stuff. Looks like that's what we're going to have to do here. So, non-alcoholic, by the way. It's interesting. 25% seed lip, which is made of water, natural botanical distillates, and extracts acidity regulator, which is citric acid. It's got some sugar in it. That was seed lip. And then sugar, natural tonic flavoring, quinine, acidity regulator, sodium citrate. It mm, it's alright, it's alright. It's just very, very bitter. Let me have a break for a sec. Feeling a bit tired. We're good, but this is good, this is good. We haven't stopped, Joe, we haven't given up, so it's all good. It's just a lot of blah 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 to get through, which I'm sure won't be blah blah blah. As soon as I understand, it'll be like, oh, this is great information. Everyone should know this stuff, you know. But when I'm trying to get into it, it's just like, oh, like why don't you just say it this way, kind of thing, you know? And then you realise, well, I don't, because it's missing all the nuance. But I suppose it's always beneficial to read through all the original books that these physicists write, because I bet within them they have beautifully obvious intuition and direction, and yet here it's summarized in such a bloody ABC form. You can't quite see how we got there. Whereas if they're kind of talking about some experiment or something, you're like, oh, okay, I see why there's a number here, there's a partial differential here, and blah blah blah. Okay, I was a little bit high on my blood sugars. Right, okay, cool. I'm diabetic, if this is new to you. Let's look at this again. So we're looking at freeform. So let's start again. In its free form, oh, I see. So this is taking me down to the bottom here. So maybe I won't know what that is until I understand the rest of this. So in its free form, or including electromagnetic interactions, still on the same page, so it's taking you to the kind of explanations of those. Okay, cool. It describes all spin-half massive particles. Massive, meaning with mass, not big. So let's take a look at this do-raggy. Spin-half. For a mathematical treatment of spin-half, see spinor. Spinor. Spiner. Oh. That's like a, that thing. Whatever that's called. That's like a... What the bloody hell is it called? Starts with M. It'll come to me. In quantum mechanics, spin is an intrinsic property of all elementary particles. All known fermions, the particles that constitute ordinary matter, have a spin of half. The spin number describes how many symmetrical facets a particle has in one full rotation. A spin of 1/2 means that the particle must be rotated by 2 full turns through 720 degrees before it has the same configuration as when it started. Now we know this. I can't remember the goddamn name. Paper that you cut and twist. Starts with M. Mandalay. Mobius strip. That's the one. Mobius strip. Well done, Google. Mobius strip. All right. So, this isn't my doing. This is Tim Nguyen again, which is amazingly relevant here. This is great. Thank you, Tim. I really appreciate you. Really, really. So a Mobius strip, which I'm sure you've heard of before, is where you have this piece of paper, right? And it has a positive side and a negative side. And what happens is if you rotate it, so it's now, let's say this is stage 2, so you kind of bend it like that, and then you know that would look a bit like that. God forbid I can actually draw. Let's try that again. Something like that. Yeah. Okay. God. Right. So imagine you were to glue them. At the moment, you've still got this kind of division here where the thing is positive at the top, right? But here's the thing. Now, where's my thicker brush? There we go. Here's the thing. Now, if you do the correct way for a Mobius strip, what happens is you get really pissed off because this doesn't work. Here we go. You kind of okay, let's try this again. So you've got this, that is not a Mobius strip there, okay? So you end up with doing this rotation, but then you're going to rotate the end. So like this. So that means that you've rotated just the ends, and so this kind of ends up over here, and this kind of ends up over here. And now the plus is at the bottom and the minus is at the top. But the plus is at the top and the minus is here, right? So if you were to go round, it's saying, well, if you kept going round, you'd go to here, which would be negative, it would be positive. But then if you carried on around that strip, you'd be the other side, and you come back round here, and then you'd be on the negative side, and you go back around, and then you'd be at the original value. So you've actually, let me just try and see because my drawing's crap. Um, yeah, you can see it here. If you continue this round, it's going to kind of do this sort of thing. And then I'm here now. I'm at the bottom now. You see, I've gone round to the bottom. So now I'm up this way, and I'm going around the back. And then if I continue, I'm back where I started, which is the positive. I had to go around twice to get to that same position. So this Mobius strip, this geometrical state, says you have to go 720 degrees around that circle, that circular strip, in order to spammer. Sorry. You have to go around that circular strip in order to get to your same location. So this is spin 1/2 because I'm guessing it only does half a spin for the 360 degrees that it originally should go round. Cool. Something like that. I'm not sure about this diagram. It's a bit confusing to me. Anyway, so that's what that is. It's an intrinsic property of all elementary particles. So all particles have a spin of half. That means they have to do that double loop to get to something that you can recognize again. The spin number describes how many symmetrical facets a particle has in one full rotation. A spin of 1/2 means that the particle must be rotated by 2 full turns before it has the same configuration as when it started. Particles having net spin half include the proton, neutron, electron, neutron, and quarks. Quarks are the subs. Neutrino is a sub. The dynamics of spin half objects cannot be accurately described using classical physics. Well, I think we did a good enough job with Tim. They are among the simplest systems which require quantum mechanics to describe them. As such, the study of the behavior of spin half systems forms a central part of quantum mechanics. Stern-Gerlach experiments. So let's find out where they come from, right? How do they find them out? The necessity of introducing half-integer spin goes back experimentally to the results of the Stern-Gerlach experiment. A beam of atoms is run through a strong heterogeneous magnetic field, which then splits into n parts depending on the intrinsic angular momentum of the atoms. It was found that for silver atoms, the beam was split in two. The ground state therefore could not be an integer, because even if the intrinsic angular momentum of the atoms were the smallest non-zero integer possible, 0.01, 1. Oh, okay, integer, sorry. Yeah, smallest non-zero is 1, right. The beam would be split into 3 parts, corresponding to atoms with L sub z is equal to -1 plus 1 and 0, with 0 simply being the value known to come between -1 and +1, while also being a whole integer itself, and thus a valid quantized spin number in this case. The existence of this hypothetical extra step between the two polarized quantum states would necessitate a third quantum state, a third beam, which is not observed in the experiment. The conclusion was that silver atoms had net intrinsic angular momentum of half. A bit hard to envisage that. Let's read that again. The necessity of introducing half-integer spin goes back experimentally to Stern-Gerlach. A Stern-Gerlach. A beam of atoms is run through a strong heterogeneous magnetic field. Heterogeneous. Etymology. Hetero. Other. Genus. A kind. Other kind. An other kind magnetic field, which then splits into n parts depending on the intrinsic angular momentum of the atoms. It was found that for silver atoms, let's have a look at silver, Na, that's sodium, silver is Li, silver, can't remember now, periodic table. Oh, yeah, it's the A, isn't it? Yeah. Ag. Yeah. 47 atomic number. That means it's got 47 protons. What is that? I think special here that I can see. 47. It's not 42. Okay. So it's found that for silver atoms, 47 atomic number, the beam was split in two. The ground state therefore could not be an integer, because even if the intrinsic angular momentum of the atoms were the smallest non-zero 1, the beam would be split into three parts, because they're integers. Simply being the and 0 with zeros simply being the value known to come between, and thus a valid quantized spin number in this case. The existence of this hypothetical extra step between the two polarized quantum states would necessitate a third quantum state, a third beam, which is not observed in the experiment. The conclusion was that the silver atoms had net intrinsic angular momentum of half. I don't understand that. I don't get that. Let's see if it goes on. Oh, you know what? Let's watch a video. Stern Gerlach. Let's get a good intuition. Oh, this one. Stern Gerlach. There we go. Got it.
Booking a Verbo holiday home means having room to spread out in a place on the beach. Book today.
The Stern-Gerlach experiment, performed in 1922, delivered the first experimental proof of the fascinating degree of freedom of an electron spin. A beam of silver atoms was generated in an atomic beam furnace. It was then sent towards an inhomogeneous magnetic field. According to classical physics, one would expect the magnetic moments of silver atoms to be randomly oriented. They should be deflected in the inhomogeneous magnetic field by different amounts, depending on their orientation. However, the researchers observed that the beam was split in two possible states, which were later named spin up and spin down. How can this be explained? Let us first analyze the electron configuration of a silver atom. One silver atom has a total of 47 electrons. In 46 of these electrons, each spin up is paired with one spin down. The spins neutralize each other. There is only one unpaired spin, the spin of the 5s electron. It can be either in spin up or spin down, or in any superposition of these two states.
Closest to the atom as well, the nucleus.
We can represent this spin state using a Bloch sphere. The spin can point in any random direction. The spins of all silver atoms are randomly distributed. They are therefore not polarized. In fact, there is a close connection between this experiment with a single electron spin and the experiment with single polarized photons. Here, the polarizing filter corresponds to the inhomogeneous magnetic field. Just like with photons, in a single experiment, it is completely random whether the spin points in the direction of the polarizing filter or in the opposite direction. The result is a black and white random pattern. Let's have a closer look at the quantum mechanical measurement process in the Bloch sphere. The spin has some arbitrary orientation before it interacts with the inhomogeneous magnetic field. The inhomogeneous magnetic field acts as a filter. It is presented here as a slot. It forces the spin to take a random orientation, either in line with the inhomogeneous magnetic field or in the opposite direction. If the basis state is close to up, it is very unlikely to change the direction in down. However, it may still do so. When performing their canonical experiment, Stern and Gerlach were unable to use single silver atoms. Therefore, they could not demonstrate the role of chance in each experiment. However, they were the first to demonstrate that the spin is quantized, or separated in up and down. It was a sensational achievement in their time.
Okay. Yeah. Sure. Okay. So spin half objects are all fermions. Okay, let's have a look at this one then. In particle physics, a fermion is a particle that follows Fermi-Dirac statistics and generally has half-odd integer spin. Excuse me, my apologies. Spin half, spin 3/2, etc. These particles obey the Pauli exclusion principle. Fermions include all quarks and leptons, as well as all composite particles made of an odd number of these, such as all baryons and many atoms and nuclei. Fermions differ from bosons, which obey Bose-Einstein statistics. Some fermions are elementary particles such as the electrons, and some are composite particles such as the protons. According to the spin statistics theorem in relativistic quantum field theory, particles with integer spin are bosons, while particles with half integer spin are fermions. Understood. Okay, cool. So it describes all spin half massive particles. Such massive particles. The term massive particles refers to particles which have non-zero rest mass. According to special relativity, their velocity is always lower than the speed of light. The synonyms bradion, from Greek bradis, slow, tarion or ition, are sometimes used to contrast with luxon, which moves at light speed, and hypothetical tachyon, which moves faster than light. The term mass refers to which have a non-zero mass. Okay. Such as electrons and quarks, for which parity is asymmetry. It describes all spin half massive particles such as electrons and quarks. What's a quark? Type of elementary particle, fundamental constituent of matter. Quarks combine to form composite particles called hadrons, the most stable of which are protons and neutrons, the components of atomic nuclei. All commonly observable matter is composed of up and down quarks and electrons. Owing to a phenomenon known as color confinement, quarks are never found in isolation. They can be found only within hadrons, which include baryons, such as protons and neutrons, and mesons, or in quark gluon plasmas. For this reason, much of what is known about quarks has been drawn from observations of hadrons. Quarks have various intrinsic properties, including electric charge, mass, color charge, and spin. They are the only elementary particles in the standard model of particle physics to experience all four fundamental interactions, also known as fundamental forces: electrogravitation, strong and weak, as well as the only known particles whose electron charges are not integer multiples of the elementary charge. Let's get a little ABC on that. A quark is a type of elementary particle and a fundamental constituent of matter. So such as electrons and quarks, for which parity oh, okay. I thought parity was same as, but clearly not. What's called parity inversion is the flip in the sign of one spatial coordinate. In 3 dimensions, it could also refer to the simultaneous flip in the sign of all 3 spatial coordinates, a point reflection. So, such as electrons, so when it's flipped, it's symmetrical. So the Dirac equation is describing spin half particles which are symmetrical when flipped. Spin half particles, symmetrical when flipped. Okay. So does this help us? Because we are studying electrons and protons with neutrons because of their small mass. Neutrons have no charge, but they have a mass. A mass I could do with the curvature, the relativistic stuff. And electrons are great. Okay, so protons and quarks. Well, protons are made of quarks, so maybe that's not a problem then. Okay, cool. Because I'm just trying to think if this is the equation that we're going to need to deal with in our venture. It is consistent with both the principles of quantum mechanics and the theory of special relativity. It was the first theory to account fully for special relativity in the context of quantum mechanics. It was validated by accounting for the fine details of the hydrogen spectrum in a completely rigorous way. The emission spectrum of atomic hydrogen has been divided into a number of spectral series with wavelengths given by the Rydberg formula. These observed spectral lines are due to the electron making transitions between 2 energy levels in an atom. The classification of the series by the Rydberg formula was important in the development of quantum mechanics. The spectral series are important in astronomical spectroscopy for detecting the presence of hydrogen and calculating redshifts. A hydrogen atom consists of an electron orbiting its nucleus. The electromagnetic force between the electron and the nuclear proton leads to a set of quantum states for the electron, each with its own energy. These states were visualized by the Bohr model of the hydrogen atom as being distinct orbits around the nucleus. Each energy level, or electron shell, or orbit, is designated by an integer n as shown in the figure. The Bohr model was later replaced by quantum mechanics, in which the electron occupies an atomic orbital rather than an orbital. But the allowed energy levels of the hydrogen atom remained the same as in the earlier theory. Spectral emission occurs when an electron transitions or jumps from a higher energy state to a lower energy state. To distinguish the two states, the lower energy state is commonly designated as n first order of n, and the higher energy state is designated as n. The energy of an emitted photon corresponds to the energy difference between the two states. Because the energy of each state is fixed, the energy difference between them is fixed, and the transition will always produce a photon with the same energy. The spectral lines are grouped into series according to derivative of n. Lines are named sequentially starting from the longest wavelength lowest frequency of the series using Greek letters within each series. For example, the 2, 1 line is called Lyman alpha, while the 7, 3 is called Pascan delta. There are emission lines from hydrogen that fall outside of these series, such as the 21 centimeter line. These emission lines correspond to much rarer atomic events such as hyperfine transitions. The fine structure also results in single spectral lines appearing as two or more closely grouped thinner lines due to relativistic corrections. In quantum mechanical theory, the discrete spectrum of atomic emission was based on the Schrodinger equation, which is mainly devoted to the study of energy spectra of hydrogen-like atoms, whereas the time-dependent equivalent Heisenberg equation is convenient when studying an atom driven by an external electromagnetic wave. Okay. In the processes of absorption or emission of photons by an atom, the conservation laws hold for the whole isolated system, such as an atom plus a photon. Therefore, the motion of the electron in the process of photon absorption or emission is always accompanied by motion of the nucleus. And because the mass of the nucleus is always finite, the energy spectra of hydrogen-like atoms must depend on the nuclear mass. Makes sense. So, okay. I think we've got this first paragraph. It feels like there was a lot in it, but most of it's technical, so not sure I need to get all of those details quite yet. So I think I'm going to leave it there for now, actually. That was good. Let's move on to paragraph 2 after. I think what we'll aim for is to write this equation in code. So we're going to need to do a few trials with some data, get the numbers to work, check them against experimental data, and then we'll move back on to orchestrating some architecture around our program. And finally, let's not forget about Schrodinger here, the Schro boy, because in a way, understanding this seems rather relevant given its equality to the Dirac equation. So it's just that this takes into account this curvature energy thing, mc squared. Just a quick one. I understand all of this apart from that beta, so I'm really looking forward to knowing what the beta stands for in this equation. Let's stop there. I'm really tired, and I really appreciated you, and as always, keep loving and keep learning. It is the only way. So, tally ho, speak to you later.